Okay, so that was the one-dimensional unitary group U1. Now let's go the next dimension up and consider the group U2. So I just forgot to make a quick comment about U1. We saw that we have a special refinement, which is now the set of matrices that have to have determinant +1. So what's the special refinement of the group U1 going to be? Well, we kind of saw that the U1 group is just trivially 1-by-1 matrices, or just single complex numbers. And so taking the determinant of a single number doesn't really make too much sense. But instead we just realised that the special refinement of U1 is just really the same thing as U1. So SU1 and U1 are really the same group. And so we never need to really worry about that difference between SU and U in the one-dimensional case. So that was the one-dimensional unitary group. Now let's have a look at the two-dimensional unitary group. So of course we're going to use our general definition again, and just to save a bit of space, since I'm going to need quite a lot, I'm just going to write on top of the definition. So we're going to look at the group U2, which is now the two-dimensional unitary group. So it's going to be subset of the 2-by-2 matrices with complex entries that now have to satisfy n dagger times m is the identity, or our unitarity property. So I'm actually going to ignore the unitary group and just jump straight to the special unitary group, as it's really where all the interesting stuff is going to be happening. So I'm just going to add in my other condition that we know comes from the special refinement. And so now we're going to want to come up with some set of complex matrices that satisfy both of these requirements. And now there are a number of ways that you could go about doing this. You could, first of all, start with the group U2, work out what the matrices are going to be that satisfy this condition. You'll find some fairly nice constraints on the matrix elements from this condition, and then using this condition you'll be able to solve and come up with the general form of any SU2 matrix. But rather than plugging and chugging through all that quite nasty algebra, it really is just algebra, and it's going to be probably, I think, too confusing to do on the board, but I would encourage you to have a go yourself. What I'm going to instead do is just postulate the form that our SU2 matrix is going to have, and then we're just going to check that it does satisfy these requirements. So I'm just now going to postulate our matrix M is going to have the following form. And so now let's check that this is an SU2 matrix. So first of all, we need to remember that these A and B are both complex. So just looking at the form of our matrix, we can now kind of see that we only have two free complex parameters, because we've been able to somehow reduce our four matrix elements into two matrix elements. This is going to come somehow from this condition. But now let's just check our conditions and make sure that they're satisfied. So we need to have that m dagger m is just the identity. So m dagger, we have to conjugate and transpose. M dagger is going to have the following form. And so now let's just multiply them out and see what happens. Okay, so we're going to get a dagger A plus B, sorry, A bar A plus B bar B, which is just mod A squared plus mod B squared. Now we're going to get A bar B minus B A bar. And then similarly down here, B bar A minus A B bar. And then again, the final column, we're going to have a b squared plus a squared. And we know that this matrix now has to be equal to the identity. So I'll remind you the matrix we were postulating was of the following form, and now we're checking this condition. So comparing against the identity, we can see that this term, mod a squared plus b squared, is going to have to be equal to 1 in the identity matrix. And then our off-diagonal components are going to have to be 0, which we can already see is true because this is just a bar b minus b a bar. And of course these numbers commute. And so this is okay. We just need to realise whether or not this condition is true. But now we can use our determinant expression to further realise this. So if we just take now the determinant of n, we're going to get an, sorry, that should have been an a bar. We're going to get an a bar, so just mod a squared. Now minus b bar, so just then plus the mod b squared. And our determinant has to be equal to 1. So yes, we have effectively now realised that this condition is going to be true for this matrix. And so we've checked both of our conditions, and so yes, a matrix of this form is now a general SU2 matrix. So that's good. And as I said, you could have arrived at this expression by just saying that we take a general matrix from GL, and then you impose these restrictions on this general matrix, work out all the algebra, and you'll find that somehow these C and D components are in fact redundant and they're just related to the A and B components somehow. And then we can realise that the matrix is going to have this form. And so as we can see, our SU2 matrix is now just simply dependent on two complex parameters, A and B. But of course we know that these two complex parameters now are going to somehow be corresponding to some four-dimensional object. So let's have a little look at what that's going to look like now. So let's just first of all realise what I'm meaning by this. I'm saying that now any SU2 matrix we can just express in terms of its matrix elements, A and B. And so if I let these two now variable axes kind of correspond to A and B, any SU2 matrix is just going to be lying in some point now in this space C2. And what we of course need to realise now is that this C2 is of course isomorphic to R4, because each of these complex dimensions is now two real dimensions. And so any point given by the coordinates AB in this two-dimensional complex space is just going to be a point in R4. And so the matrix elements we can now represent by points AB in this C2 R4 space. And so now let's have a look at what this topology is essentially going to give us, or what are all of these points going to look like in the space R4. So just reminding you that a point now in this C2 parameter space, if you like, is just the SU2 matrix that we can kind of calculate using these 2 points in this way. So I'm effectively just giving now the coordinates of an SU2 matrix, and we can kind of think about it as lying on this two-dimensional complex plane, or rather a four-dimensional real space. So let's exemplify the 4 dimensions now. If I now introduce not 2 complex parameters but 4 real parameters by saying that the complex number A is going to be some coordinate x plus iy. Remember, this is using my identification that the complex plane is the same thing as R2. So we're going to have now two coordinates. A is x plus iy, and B is going to be z plus iw. That maybe looks too much like an omega. So w. So these are now going to be my four real coordinates of R4. And we're using these four real coordinates to represent the two-dimensional complex space. But let's now see what these conditions are going to say, or how these conditions are going to translate now into these real parameters. So remember our condition that we had, that the modulus of a squared plus b squared has to be equal to 1. Let's now see what this looks like with these real parameters. So the modulus squareds of these complex numbers are really quite simple to calculate. Just to remind you, to take the modulus squared, you're essentially calculating the product of a complex number with its complex conjugate. And so just now subbing in the definition of A, this is going to be x minus iy, x plus iy. And so this modulus squared is simply just going to reduce to x squared plus y squared. Just expanding out the brackets, all of the i's are going to cancel. And so what we can realise this condition is now saying is the following. So we're going to have that 1 is equal to x squared plus y squared. That was the modulus of a squared. And then the modulus of b squared is going to give me z squared plus w squared. So just so you're absolutely clear what I'm doing, I'm taking these complex coordinates, expressing them using two real coordinates, and then I'm just realizing what this condition on our complex coordinates is going to translate to on our real coordinates. And we found that we get this condition, and now you just have to kind of realize what this condition is now describing is the 3-sphere S3, which as a manifold kind of lives in the space R4. And one of the ways you can realize the 3-sphere is simply just by realizing that it's all the points in R4 that now satisfy this condition, just kind of making its lower dimensional analogy. If we say ignore two coordinates, we're now just talking about effectively the sphere in 2 dimensions. And so that's going to be x squared plus y squared, which is just describing a circle. And then x squared plus y squared plus z squared is describing the surface of our 2-dimensional sphere, which of course lives in 3 dimensions. And then just in complete analogy, this is now the 3-dimensional sphere, which exists in 4 dimensions. So this is now telling us that any point x, y, z, w in 4-dimensional space that satisfies this condition is going to correspond to, well, first of all, 2 complex coordinates, which then corresponds to an SU2 matrix. And so all the elements of SU2, just all the possible coordinate values that these A and B's could possibly take, they're going to lie somewhere on this, if you like, solution condition. And so any x, y, z, w corresponding to A and B that lies on the surface of this 3-sphere are now direct correspondent with an element of SU2. And so what this means is we've now identified another isomorphism, the isomorphism of the group elements of SU2, now with the points lying on the 3-sphere. So now, topologically at least, this set of elements, SU2, is now topologically equivalent to our 3-sphere S3. Because essentially now, any SU2 element, M, we can basically just express it by giving 2 complex coordinates. And we've now seen that the constraints on those coordinates are going to, well, first of all, they're going to correspond to constraints on the resulting real components of that complex coordinate. And we've now seen how this translates to this condition, which we can realize as being essentially now all of the points which lie on the 3-sphere. So to summarize then, we started looking at the next unitary group up in the list, SU2. And we didn't really bother looking at U without the S refinement. We just went straight to SU2 as it's really the more interesting version. And then I simply just postulated this matrix, but we could have instead started with a general GL2C matrix and then used these requirements to impose restrictions. But rather than getting messy with the algebra, I just simply postulated this and then showed you, or we checked, that it is going to satisfy both of these. And so that led us to the realization that any SU2 matrix is basically able to be parameterized by two complex parameters, A and B. And then we were able to realize, using our convenient identification, that complex spaces are isomorphic to two-dimensional real spaces. And so this two-dimensional complex space is isomorphic to four-dimensional real space. And so by effectively expressing each of these complex coordinates using two real coordinates, we could translate the constraints on the complex coordinates onto the real coordinates. And we found that this now is describing the topology of this 3-sphere, which is kind of embedded or living in a four-dimensional real space. So any element SU2, which can be given by these four real numbers, just corresponding now to these two complex numbers, any element of SU2 is just simply an element that lies on this 3-sphere. Now, of course, the geometry of the 3-sphere is quite wildly complicated, and we can't really visualize geometries in 4 dimensions, but we have now just a very concrete and algebraic understanding of this relation. So in the next few videos, we're going to see how this group SU2 is quite fundamentally connected with these new things which we're going to discover called spinors. And we're going to be able to see that, well, first of all, the group SU2 is obviously now going to be the symmetry group of the 3-sphere. And we're going to see that we can understand these spinors as being acted on by SU2 elements. And so we can just identify that spinors are then going to be lying somehow on this unit 3-sphere. But that's all coming up. Just now, this is how we understand the group SU2 algebraically.